couple of people. Okay. Good evening, everyone. My name is Jue Wang from Tencent AI Lab in China. This is Asiagraphics Web Seminar Section 4. Today we have two speakers. We have two very interesting talks about image restoration, image deblurring. So the first speaker is Seungyong Lee from Post-Tech Korea. Seungyong is a professor of computer science and engineering at Post-Tech. He received a PhD degree in computer science from KAIST, and then he did postdoc in New York, and later he visited, during his sabbatical years, he worked at MPI Informatics and also Creative Technologies Lab at Adobe. That's where I used to work. So we knew each other for a long time, and we collaborated on many interesting projects. So he's probably the most famous work is image deblurring and photo upright adjustment. So today he's gonna talk about image defocus deblurring. So let's see what he's going to talk about. Okay, now it's your turn, Seungyong.
Okay, yeah, thank you. Thank you for the introduction. And the defocus happens by the shallow depth of field. That means some part of this image is very sharp, this part. Some other parts are blurry. Yeah, this defocus blur is caused by some circle of confusion. That means that this is some simplified camera model. And we have some focal plane. Focal plane means that the object at the focal plane will be very sharp on the image sensor, image plane. But some other object up from this focal plane will be blurry, because you can see that one point on this defocus plane will be mapped onto some circle, not a single point. Then we have some blur. Then also from this diagram, you can see that the defocus blur depends on the depth from the camera sensor, okay? Then also the defocus blur is caused by the circle confusion. That means that the blur shapes are similar among different pixels, even though the blur size depends on the depth and can spatially vary. The defocus deblurring means that we want to restore all in focus image from a defocus image. Here, yeah, obviously this is better than this one. Then also this defocus deblurring can help some image recognition task. For example, here you can see this segmentation is much better when the input has been defocus deblurred. But there has not been a lot of research on this defocus deblurring using deep learning. And also we can compare this defocus deblurring with the motion deblurring. I mean, already Junshan mentioned this deblurring problem. Here, this is a typical example of motion blur. Motion blur means the image is blurry because the camera was shaken through this trajectory. But in this example, the corner is like a trajectory. That means we have some 1D integration of pixel value in this blurred image. But in contrast, in the case of this defocus blur, we have this, I'm not sure you can see my mouse, probably not.
Yes, we can see it.
Okay, great, yes. Then here, the defocus blur corner is like a disc shape. That means more pixels are merged to produce this defocus blur. That means this defocus blur is probably more similarly reinforced than motion deblurring. Then also there is no big data set for defocus blur, and then it's not easy to apply deep learning to this task. Yeah, traditionally, we used this two-step approach. That means in the first step, we estimate the defocus map. That means we assume some kind of some typical shape of defocus blur, such as disk or Gaussian blur. And then defocus map estimation can give us the size of a blur at each pixel. And then we apply some non-blind convolution to obtain the final focus image. But in this case, usually the defocus map estimation is not perfect, and also this simple assumption of disk or Gaussian shape of defocus blur is not very accurate, and the result was not perfect. Recently, end-to-end deep learning method has been proposed for defocus deblurring. The technique was based on this DPD. The technique is DPDNet, and it was based on a data set that contains some dual pixel defocus deblurring images. That means here, as you can see here, we have some two images, like dual pixel stereo defocus image, like left and right defocus image. And then they also have some ground truth. Then their network, this kind of network, is trained to produce this orient focus image from this merged defocus image. That means they produce one single defocus image from this stereo defocus image, and then the network is trained to produce this one from this one. But in this paper, they simply use some standard UNet structure, and the network didn't fully exploit the property of defocus blur, and then the performance has some rooms for improvement. And recently, I worked on this defocus deblurring problem, and today I will introduce two of my recent papers on the topic. The first one is about the iterative filtered network for defocus deblurring. Then here, we simply try to design some speculative network for defocus deblurring. Then our key idea is to estimate some adaptive filter. Adaptive filter means here we have some input image and we have some feature encoder. Then we want to deblur these features basically. But instead of directly estimating defocus features from this encoded feature, instead we predict some filters needed for defocus deblur. Okay, then, and this IFAN is our model to predict this adaptive filters, and this will be our filter. And then we apply this filter to this encoded features, and then we produce some defocused features, and then eventually the defocused feature will be used for decoding to produce this final output. But that is the main process. Then our main idea lies at this iterative filtered network to produce this adaptive filter FD blur. And this FD blur is basically consists of some stacked separable deblurring filter. Then this filter should be spatially varying, because at the beginning I mentioned that the defocus blur will change depending on pixels. Even though their shapes are similar, their size or scale will vary depending on the depth from the camera at each pixel, right? Then our predicted filter should be spatially varying. And then to handle this spatially varying filter, we use this iterative adaptive convolution. This iterative adaptive convolution consists of separate filter, and also we apply the separate filter iteratively. Then basically, by having this separate filter, we can handle some larger receptive field. That means when we want to have some larger receptive field, we have to have some larger corner. But having a larger corner means we need some more memory, right? Then here, by having some separate filter, we can reduce the memory requirement and still can handle the larger receptive field. Then also, when you use some separate filter, we may have some error because separate filter maybe could be less accurate than the ordinary filter. Then to resolve those possible error, we apply this filter iteratively. Then we can handle the error caused by this separate filter. Then basically, yeah, that was the idea. Idea was that here we encode a feature and we apply this. We have this IFAN module to predict this iterative separator filter. And then we also some other component in the network training. One is the disparity map estimator. Yeah, at the beginning, I mentioned that the defocus blur size depend on the depth or distance from the camera. Then also we know that the depth from the camera is related to disparity in the case of stereo image, right? But in our data set contain dual pixel images. That means we have left and right stereo images, right? Then we use that stereo image for this training of our network. Then here in our network, we have some disparity map estimation module. And here we estimate the disparity, which is related to depth, and also that disparity also related to defocus blur size. Then by having this disparity map estimation, we can have more accurate prediction of this deblurring filter. But this dual pixel image needed only for training. Generally, in our test phase, we do not have dual pixel images. Then, but in this in our setting, this dual pixel image is only needed for training, and in the test phase, we do not need this dual pixel images. Then here, we can see some example of disparity map estimation. Accurate disparity map estimation means accurate estimation of defocus blur size. Then also to further increase the performance of our network, we also have some deblurring network. This is it. Then here we predict the filter corner for deblurring, but from that corner, we also try to estimate the regular corner. That means here, this is the regular corner. Then when we apply this regular corner to the input, we get the ground truth sharp image, we get the blurry image. Then the reason for this reblurring is that if we can successfully reblur this sharp image to the original input, that means this deblur filter contain some enough information about the blur shape and size, right? Then this deblurring network can help to train our IFAN model to predict more accurate this deblur filter. And in summary, we have this network structure, and by having this disparity map estimator and deblurring network part, we can obtain better performance of our network. In the training page, we use this DPDD training set that contains some dual pixel captured by Canon EOS camera. And this data set contains some pairs of defocus image and all-in focus image. Then we can have some supervised training. The object function contains these three terms. Then here, IB is a defocus input, and I mentioned that this data set contains the dual pixel stereo image, and then this is the output. this liberal loss means with the reconstruction loss, our network should produce a defocus result similar to ground truth. And this is about the disparity map estimation. Then our disparity estimation should produce some proper disparity. Proper means here means that when we apply the disparity to the left image, the left image should go to the right image or the other way around here. And also reblurring error means that when we apply this reblurring filter to the ground truth sharp image, we should get the original input blurred image. By having these three objective functions, we can train our network nicely. And this is the result. First, we show some aberration study result. So when we have this disparity map estimator, we have some improvement in the accuracy. Then this part is about the iterative filter prediction. And then this part is a reblurring network. Then you can see by adding this component one by one, we can obtain some increased performance of our deblurring network. This is a comparison with previous work. You can see that our network achieved the best performance. Then interestingly, this DPD-NET-D is using dual pixel, which means stereo pixel image for defocus deblurring. But our network use only single. We do not use those stereo input, but even in that case, our network can show better performance than this one using dual pixels. Then also you can see here, in terms of computation cost, our network has a smaller number of parameters and runs faster. This shows some like a qualitative comparison. Here you can see this is the best result, best previous result, and then ours better. Then also here you can see ours is better than the previous one. Okay, and to test the generalizability of our network, we built some real defocus blur test set. Here, this is a test set because we only capture 50 pairs. I mean, taking this real defocus blur data set is not easy. Then we simply take small number of examples. Then we use it for only testing, not for training. Here we have this dual camera system like this. We have some beam splitter, and the input light is splitted into two parts, and we have two cameras, and one is captured ground truth, and the other is capturing some defocus blurred image. Then this is another pictures. And then here we have some like a test set. When we use those test set for previous method and ours, we can see that ours works best in terms of like PSNR, SSIM, and some other measures. And this shows some qualitative comparison again. This is the input, and this is the result of previous work, and then ours is much better than previous one. That was the first paper. Then in the paper, in summary, we proposed some network architecture, and then we proposed some training scheme, and also we built some real data set for testing. Yeah, that was kind of good, but still we have some concern, or we are not quite very happy about the previous result, because we realized that even though the network works very good for defocus deblurring, still the network does not fully exploit the inherent property of defocus deblur. you remember at the beginning, I mentioned that in the case of defocus blur, the blur shape is similar, but even though the blur scale can change depending on image pixel position, right? But in the previous paper, we only use spatially varying property only, but not specifically some specific inherent property of defocus blur. Then in this paper, we try to exploit this specific property of defocus deblurring based on inverse corner. Okay, then simply we found this property. Inverse corner has some similar property to the original defocus blur corner. I will explain the property in more detail shortly. Yeah, let me first briefly explain what the inverse corner is. This is a typical blur equation. This is a blurry image, and then this is corner, and this is sharp image, and this is noise, right? And here you see it, and then we usually use convolution for displaying this Deblurring model. Then when we apply this Fourier transform to both sides, we get this one, ignoring this noise part. And then here we want to obtain this x, and by manipulating this equation a little bit, and then we get this one. Here we move this one here, and then we apply inverse Fourier transform, we get this one. And then we can take out this part, and eventually we get this one, right? That means in terms of Fourier transform and inverse Fourier transform, we can obtain the final, our desirable sharp image by using this inverse corner, means here by convolving this inverse corner to the input image, right? And this is the inverse corner. Then here you see that this inverse corner can be obtained by applying some Fourier transform and inverse Fourier transform. And as you just saw, yeah, deblurring or deconvolution can be handled by applying inverse corner. But when we try to use it, we found that you will see that usually the inverse corner size, inverse corner is much larger than the blur corner. Then also the convolution with inverse corner is very sensitive to outlier. Then here you see that some artifact when we obtain this deblurring result by inverse corner. But still, when we use CNN, like convolution neural network, this concept of using inverse corner for defocus blur or deblurring may work quite well. Then we try to use this concept of inverse corner in our in this paper. There are some key ideas. The first one is that when the scale of defocus blur changes, here again, you remember I mentioned that in the case of defocus blur, the shape remains almost same, but the scale is changing. When the scale of defocus blur changes, the shape of the corresponding inverse corner remains the same, but only the scale changes. That means here we have this corner for defocus blur, and then we upsample. That means same corner but with different scale, and then we take the inverse, we obtain the inverse corner, then we get this one. But this is the same as this one. This one is obtained by, we have this corner, and we obtain the inverse corner, and we upscale. Then this is the same, okay? Then also we can verify that using some example here. This is the result obtained from this one, and this was from this one. You can see that they're almost same. But what does that mean? That means that in this defocus blur image, we have small defocus blur here, middle, and large, right? Then we can apply inverse corner to remove defocus blur from this part. Then in that case, the inverse corner needed for deblurring this part and this part and this part will have the same shape, single shape, then only the scale may change, right? Yeah, that is the meaning of the first key idea. Again, to deblur these different pixels, we can use the same inverse corner, but only the scale of the inverse corner need to be changed. The second key idea is about how to represent all the different scale of inverse corner. Yeah, it may be hard or impossible to represent all the different continuous scale of inverse corner. Then we simply use some discrete set of inverse corner. Then we do some interpolation. Yeah, in this example, to handle the focus blur of this image, we need this kind of scale of this inverse corner. But we approximate this scale by interpolating this small scale and large scale. And here, this example shows that this is a result of applying this inverse corner to this one, and we obtain this one. Then by applying this inverse corner to here, then we obtain this one. Then by interpolating these two images, we can obtain the result of applying this inverse corner to this one. Okay, then that means that when we apply this inverse corner to defocus deblur this image, we apply some discrete, some large, middle, and small scale of inverse corner to this one. And then we can interpolate the result of this convolution. Then here, for example, this part is a large defocus blur, and then we apply this. Then let me make it clear. Then here we apply these three scales of inverse corner, and we obtain three images. Then we interpolate using some weights. Then for this part, the result of this inverse corner will have a larger weight because it has a larger blur. Then here, this part has a middle scale blur, and then the result of this middle scale inverse corner will have a larger weight, and this part is handled by this smaller scale inverse corner, something like that. Then here, this means that we deblur this input by using different scale of inverse corner, and then we interpolate using some weight depending on the defocus blur size. The last idea is that we have to represent this different scales of inverse corner, but it's not very immediate. It's not very straightforward. But we found that if we use this dilated corner, then this dilated corner will have the same component in the corner, and then it's easy to share the same weight for this in this dilated corner. That means by having this dilated corner with the same weight but different scale, we can represent same inverse corner but with different scale very easily. Okay, then here, this example shows that this is a sampled inverse corner with a larger scale, and that this is like a spatially sampled inverse corner with this larger scale. But when we apply these two, this one and this one to this input, we obtain very similar deblur result. That means this dilated corner is enough to deblur this given input blurry image. Then we designed this network using these three key ideas. Yeah, basically, we approximate this equation. You remember this equation here. We approximate this equation using some network. Then we first, but we do that in the picture space. That means we have some encoding and decoding part, and we process this encoded picture using these layers. Then this layer is a convolution layer approximating inverse corner, but they have the same weight. They share the same dilated corner, but with different scale. And then we have some spatial scale attention model. Then here we have some interpolation of alpha value. Then this scale attention determine this interpolation factor for these different scales of inverse corner. Then by having the scale attention, we can handle different scales at each pixel. And also we have some channel attention. Here we call shape attention. That means this inverse corner has multiple channels, and then by having some channel attention, we can handle slightly different corner shape among the different pixels. Then this is our final network structure. And then for training the network, we use the same data set used for previous paper. Then object function is very easy, like reconstruction loss and perceptual loss. And then this result, then first we can show that by sharing the weight means that we assume the inverse corner is the same shape. Then we share the weight among different scales of direct corner. And then by sharing this weight, we can obtain some better accuracy. And also here we have some component like a directed convolution unit for inverse corner and the scalar shape attention. Then this number show that each component has some help, has some roles in improving the accuracy. Okay, and then here you see that I mentioned that scale attention is determined the weight for interpreting different corner scale. Then for example here, this part has a very large defocus blur. That means the dilation rate 5 has some higher weight. And we can have the clear Deblurring result here. This is a comparison with some other previous work. Then here you can see our network produced the best result. Then more importantly, our network is very simple. Here you can see that our network is very fast and it has very small number of parameters compared to previous work. Because our network is designed by fully exploiting the specific features of the Defocus Deblurring. There's some other result. Then here you see that by comparing this result, and you can see that our result is better than previous ones. Yeah, another result, and ours better. Okay. Yeah, today I introduced some two novel single image Defocus Deblurring method. The first one is based on this iterative filter adaptive network. And the second one is based on corner sharing parallel atlas convolution. And here, both of them can produce orient focus image, as you can see here. When we compare these two techniques, the first one has some more capability, right? The network structure is more complicated than the second one, as you can see here. Then it has more capability. Then we also introduce some training strategy, such as a disparate map estimation and Deblurring module. And it works well. It's powerful. But the limitation of this technique is that the network is too big, kind of like complicated. In contrast, the second approach is based on fully exploiting the nature of inverse corner for Defocus blur. And then the network is very simple. Then the training is easier, the inference is simple. Then even though it's not as powerful as the first one, it can handle mostly common shapes of Defocus blur. And then there are some pros and cons, but generally this is more compact and probably more useful in practice. Even though we proposed two new techniques for Defocus Deblurring, we still have some limitation. Here, this part is kind of like a saturation, the overexposed part. And also here we have some different shapes of Defocus blur. And then in those cases, like some irregular shape of or strong highlight may have some difficulty to our technique for defocus deblur. Then probably in the future, we can generate a data set containing various types of defocus blur, and then we probably or hopefully we will be able to handle more general kinds of defocus blur. Okay, that was it. Yeah, thank you, and I hope there are some questions.
Yeah, thank you,
I'll be happy
Seungyong.
to answer. Yes.
Yeah, very, very nice work. Very interesting
Thank
ideas.
you.
I think one thing I'm impressed most about your work is that you always kind of pay attention to the computational cost of the method. So,
sure.
So you always, yeah, I saw many of your work that the resulting models are small, compact, and runs pretty fast. I think that's pretty important for real world application.
Yeah, you know that I'm mostly interested in real application of my technique.
Yes, that's good. And also, as the first work, actually, in the concept, it's very similar to Jin San's idea of physics-based models, because you also have a blur model, like a blur process, like a in the training process, use that linear blur model to. So yeah, it's
this part, yes.
Yeah, conceptually it's very similar to Jin San's work. So I guess if I mean good methods, I mean people are often find that if something really works, then people will find it in different ways. Yeah, that's good. So I do have a question here. So about training data, you used dual pixel images, right?
Yes.
I guess to me, dual pixel images are kind of like stereo pairs with a very small baseline.
Yes, exactly.
So I was wondering if someone don't have a dual pixel camera, can they kind of use a regular stereo pair, like a camera setup, to capture images and train the network? Is that gonna work?
Okay. Yeah, I think it's very good idea actually, because when we have some stereo images, we can estimate the disparity, and then we can estimate little depths, right? We can estimate depth, and then we can estimate the size of defocus blur. Right. And then that can be a good data set for training this kind of defocus deblur. Yeah, I think it's possible. Yes.
Yeah. So, but although you use dual pixel pairs, but your method in testing time, it only takes one image.
Yes. Yes.
So if you were to, I mean, if you mentioned that some other methods take two images as input.
Yeah,
right?
This one here. Yeah, this one. So this one was done by the authors proposed this data set. Then they have two versions. This one is using only one, I mean, without dual pixel, and this one is using dual pixel. Then in their method, the dual pixel based method works better. Like here, you see that. Yeah. But our technique is not using dual pixel, but even in the case, ours is better than their dual pixel method.
Right. That's good. Do you think your method can be modified to take both images?
Oh, sure. Oh, I think we. Yeah, I don't remember about this paper, but we tried it. We did that for the second paper, and then for the second paper, it worked better. Yeah, the performance got improved actually. Yes.
Right. So so also I saw that in the last slide about the limitations. I think we worked together on handling kind of highlights many years ago.
Yeah.
Right?
Yes.
Paper. But it looks like we still have this problem. Do you think it's because we we don't have a model in the kind of deep learning approach to explicitly handle the outlier, the highlight.
Yeah, I think so.
Highlights.
I think so. Yeah, I mean, as you know, deep learning is basically try to learn the mapping from the input to the output, right?
Mm-hmm.
But the highlight is only a small part of the training data, right?
Right.
And then probably, I guess, this is my guess, our trained deep neural network, and in both cases of this Defocus deep neural and motion deep neural, probably our trained deep network is trying to ignore the Defocus blur part because it's better for the network to try to handle better the majority part of the blur, which is not highlight, right?
Mm-hmm.
And I think we should some specific mechanism or some specific component that employs the deep network to explicitly handle those highlights. And without that, it will be very hard to handle this highlight.
Okay, that makes sense. We do have a question from YouTube. The question is it possible to create and use synthetic training data sets while lens simulation?
Yeah.
Path tracing with physics-based lens models.
Yeah. Yes. Today I didn't mention my previous paper, but I worked on the Defocus map estimation, actually. I mean, at the beginning, I mentioned the traditional approach use this two-step approach, right? The first one is estimate this Defocus map, and then we deblur, right? Then I worked on this Defocus map estimation. Then to do for the Defocus map estimation, we use some training set, synthetic data set, produced by actually graphics rendering using this lens model, actually. The name is the SynDOP data set, something like that. And you can find the paper and data set on my webpage. Then for the Defocus estimation, we use this thin lens model and produce a synthetic data set that we train the network. But of course, in that case, we have to handle some domain gap between this synthetic data and real images, right? Then I think we can do something similar here. That means we generate some synthetic Defocus blur data set, and then we handle domain gap. But we didn't do that because, as I already mentioned, now we have some real data set for this Defocus blur. This is a real data set. But still, the size of this Defocus blur data set is small kind of, and then we may augment this data set using some synthetic data. Yeah, I think that should be possible.
Yeah. Okay. Okay. I don't see any other questions. So let's conclude this session. First, I want to apologize for the technical difficulties we had earlier in the beginning. We didn't have a very smooth start, but I think the talks definitely worth it. With that, I'd like to thank Professor Seungyong Lee, Professor Jin-San Pan for their time and their very insightful talks. And we will see you guys next time. I think this concludes our session. Thank you.
Yeah, thank you. Thank you.
Thank you.
Yeah,
Bye.
bye.
I hope to see you soon.
Yeah, see you soon.